So that's what we'll finish off with. So by the way, a theorem in mathematics is something you should think of as a principle or a fact. It's something that you can trust absolutely to be true 100% of the time. It will always be worded very carefully and investigated to the full extent of detail that mathematics allows in order to make sure that it is always true. It's not something that's just sometimes true or usually true. It's something that is absolutely always true. So they're very powerful, and we don't take them lightly when we write them down or make them as claims. So here's the claim, though. Here's the theorem. For a homogeneous system, and by the way, you'll sometimes see me say system, and instead of writing the phrase linear system, I mean the same thing. When I say system, I mean linear system. So I might not always use the word linear in front of that. So this means a homogeneous linear system of equations. So if you have that, and if we say a little bit more, I'm going to just say with, and then I'm going to write down two things about this system. They're just going to be essentially just labels. So if we have a homogeneous system, and we let n be the number of variables in that equation, and then we let r not be the number of equations, but the number of non-zero rows in the reduced row echelon form augmented matrix. So let's write that out carefully. Rows in the RREF augmented matrix. And I can almost squeeze this in here. Just barely fit that in one line. So if you have that, we've got n is the number of variables, r is the number of non-zero rows in the reduced row echelon form matrix. This is what you can say. This is what the theorem tells you. The solution to this homogeneous system will require, well, you can tell exactly how many parameters you're going to need. It's going to be n minus r. Take these two values and subtract. Solution will require n minus r parameters. Or equivalently, another way to say this would just be to say that there's going to be n minus r free variables. So let's just pull up the previous example really quickly, just to verify this theorem in the specific case of this previous example. The theorem is true for every homogeneous linear system, so it should certainly be true for this one, which we've already worked out. And we know in advance how many parameters this one will need because we've already solved it. But let's count the variables. There's 1, 2, 3, 4 variables. So n would be 4 in this case. What about R? How many non-zero rows did the reduced row echelon form augmented matrix have? And the answer is 2, right? There were 2 leading ones, or equivalently 2 non-zero rows. So our R would be 2 in this case. So if you subtract 4 minus 2, you get 2. And guess what? That's exactly how many parameters we had, or how many free variables we had, right? x2 and x4 were both free variables, so we had a parameter for each one, so there were 2 parameters. So that confirms that the theorem that I just stated applies in this case. So that's just an example, but it's going to be true for every homogeneous system. That's the only thing you need to assume about it for this statement to be true. So remember, homogeneous just means all the constant terms are 0. So this theorem has a name. This is called the free variable theorem. For homogeneous systems. So that's the theorem. Now, one last thing I want to conclude with is corollary. And a corollary in mathematics is just a consequence of a theorem. It's another name to say this, hey, this is a really important consequence of a theorem. So if you ever see the word corollary in a textbook, it's probably going to come right after a major theorem that was stated. So it's just saying that, hey, this equivalently corollaries can be thought of as theorems as well. They're mathematical facts that are guaranteed to be true, but that the different word just indicates, hey, it's true, but it's also just, if you want to know why, it follows exactly from the theorem that preceded it. So this is no exception to that. And here's what the corollary says. So it also applies to homogeneous linear systems. So, and again, I'm just going to write a homogeneous system just to save one extra word. So if I have a homogeneous system with more variables than equations, then it's going to have infinitely many solutions. That's what this tells us. So we'll have infinitely many solutions. Well, why is that? I mean, I said that if it's a corollary, it's going to follow from the theorem right above it, but why? Let's ask ourselves why. Well, what would it mean to have infinitely many solutions? It would mean that when you write down your solution, you have at least one parameter. So equivalently, this n minus r value here, this would need to be at least 1. So for that to happen, you would need r to be smaller than n. You would need to have fewer non-zero rows in the reduced row echelon form of your augmented matrix than you have variables. Well, remember that the number of non-zero rows in the reduced row echelon form matrix, that can certainly be no larger than the number of equations that you had in the system, because the number of equations you had in the system, well, if I were to go back to this example, right, if we had 3 equations, that means we had 3 rows total in the augmented matrix. So when we go down to reduced row echelon form, the number of equations is the total number of rows. Well, at most, you're going to have as many non-zero rows in the reduced row echelon form augmented matrix as you had rows in total. So the number of equations is not going to be any smaller than r. So if the number of variables that you had is already assumed to be more than the number of equations that you have, it's automatic that the number of variables you have is going to be greater than the number of non-zero rows you have in the reduced row echelon form matrix. And that's why, so under these circumstances, you automatically have that n minus r is at least 1. So that means you're going to have at least one parameter, and that's why you're going to have infinitely many solutions. It doesn't tell you how many parameters you have, but that's not important for this corollary. But that's the reasoning, and that's why this corollary follows from this theorem. So that concludes section 1.2. We covered quite a bit of material here. It was quite a long section. Not all the sections are this long, as you'll see, but this concludes section 1.2.